Welcome back to the NGP course Seismic for Waveform Inversion. In the last tutorial I showed you how to install the Denise Black Edition code on the NEC cluster at the Computing Center of Kiel University. And today I want to show you how to model seismic wave propagation in the Mamouzi-2 model. So we are not starting right away with waveform inversion, but looking at a very important aspect of it, and that is the seismic forward modeling part. So this is really essential to understand the waveform inversion later on. So let's head right into a seismic modeling problem. And of course we could start with something very simple like a homogeneous half space. However, these problems can actually be solved analytical. So let's try something more interesting. Let's try the so-called Mamouzi-2 model. So here you can see the Mamouzi-2 model that was introduced by Martin et al. In the year 2006. Actually, it's only the central part of the Mamouzi-2 model, and I've only shown here the p-wave velocity. Actually, it is a linear elastic model, so we also have an S-wave velocity and density model. And as you can see, the model is quite complicated. So we have a marine environment, so the top 400 meters are actually a water column. Below that we have an isotropic elastic medium. The model extends down to 3.5 kilometers in y direction, and lateral extension is about 10 kilometers. You can see on the left hand side the model is quite simple. You have more or less a 1D medium, very simple layering. In the center the simple layering is disturbed by these complex thrust folds. And on the right hand side of the model you see these folded structures that are a little bit complicated. In the deeper parts you see these discontinuities of in the medium. And embedded in this medium are also hydrocarbon reservoirs. So for example, here and here we have some gas reservoirs, and in the deeper parts there are also oil reservoirs. So this is actually a very interesting benchmark problem that is widely used in the hydrocarbon exploration. So to simply check if the seismic imaging methods, or more specifically, for example, the full waveform inversion method, is actually able to resolve all these small scale structures. Now for our first modeling approach we will use a much more simplified version of this true Mamouzi-2 model. So I've downsampled the high resolution model actually quite a bit. So I've discretized the model on a Cartesian grid with 500 grid points in x direction and 174 grid points in y direction. And the grid point distance is actually 20 meters. So you can see the very coarse discretization actually also in the model. You see here these discretization steps within the layer interfaces. So that's quite obvious. And despite these simplification, we see we have actually 87,000 grid points, and at each grid point we also have 3 parameter classes because we have an isotropic elastic medium, so we have to define Vp, Vs and density at each of these grid points. So in total we have 261,000 model parameters. Yeah, that's quite a bit, but compared to more realistic models that's actually quite few model parameters, as we will see later on. So for this model we want to calculate synthetic data using the Denise Black Edition PSV module. So we are restricting ourselves to a 2D medium approximation. And of course, if we want to compute synthetic data, we have to define an acquisition geometry. And in this case, we assume that we have 100 airgun sources in the water column, to be more precisely 40 meters below the free surface. So we are assuming that a ship is traveling here on the free surface and is excitating the airgun every 80 meters, I think, along this profile. For the source wavelet, we assume a low-pass filtered spike with a maximum frequency of 15 Hz. And the seismic wave field that is excitated at each source position is recorded by 400 multi-component receivers that are laying here on the seafloor at 460 meters depth. So it's a simple OBC cable which is recording both components, so a vertical component in Y direction and a horizontal component in X direction. Okay, now we have defined the model and the acquisition geometry, so let's start modeling the seismic wave propagation in the Mamouzi-2 model with Denis Black Edition. Now before we start with the seismic modeling, let's try to organize our stuff a little bit more. Of course, you could now randomly start with the forward modeling, then do some seismic imaging, then waveform inversion for different models, then for the field data set. But in order to reproduce your results later on, it is good to start with an organization structure. So the first thing that we do is we are creating a folder for our NGP course, so NGP for waveform inversion, for example. And in this folder, I create a subfolder, which I call 001. And I call it Denis Mamouzi-2 first trial or something like that. Well, that's actually not necessary. So this will be our first Denis Mamouzi-2 modeling example. Perhaps we can call it Denis Mamouzi-2 modeling, something like that, or mod. Okay, as I said, this will be the folder for our first Mamouzi-2 modeling, and in this folder we will put all the input files, the model files, the data acquisition files. And to really reproduce it, we actually also have to store the forward modeling code that we are using. Yeah, so to make it really reproducible, you actually have to download the forward modeling code again. So we are searching again for Denis Black Edition. Go here to the code and then download it, for example, as zip file. Simple as that. And then save it in this folder here. Okay. So now we know what kind of source code, especially what version of the source code we are using for this forward modeling run. So first of all, we have to log into the NEC cluster again. That should be already a familiar task. Okay, so we're now logged in the home directory. And we go back to the working directory where we have installed the Denis Black Edition code in the last tutorial. You see it here, Denis Black Edition. Okay. So the code that you downloaded from GitHub is prepared to actually run the Mamouzi model. The problem is the model itself is not a part of this Denis Black Edition distribution, because I wanted to focus on the parameter files and the source code, and models can always be added later on. So in order to get the Mamouzi-2 model, we have to get it also from GitHub. So using again git clone and search again for the Denis Black Edition code. Okay. And then we are going to my GitHub repository, Daniel Köhn. And under repositories, you should find somewhere here a repository called Denise Benchmark. And Denise Benchmark contains a lot of benchmark problems, as you can imagine from the title, and also the Mamuzzi 2 problem. So this folder here actually contains the Mamuzzi 2 model and also the acquisition geometry and some reference solutions and so on. So we can clone again this benchmark repository. So I go to Code, then click on the clipboard to copy the repository link. And I can use also depth equals 1 again in order to only download the latest version of the code. Okay. So now we have the folder Denise Benchmark in our folder Denise Black Edition. So if I go here into the Denise Benchmark, you see we have here the Mamuzzi 2 problem. And actually we are only interested in the model files themselves. So next we go into the par directory. So from Denise Black Edition we go into the par directory. And here you can see a lot of stuff. Most of that is actually not interesting at this point. So we only have to focus on a few things. So first of all, there are a few directories that you see over here, and the most important for the forward modeling are the directories receiver, the directory source, and the directory start, and the directory su. So beside the directories, the most important file is this one over here, the Denise Mamuzzi OBC point input file. So this input file contains all the modeling parameters that are required in order to define the Mamuzzi model and the finite difference code parameters actually. And we can open this input file. Okay, and you see an overwhelming amount of parameters. I will not discuss these parameters at that point. I will go into much more detail what all these parameters for the forward problem actually mean in the next tutorial. For now we only want to run the code. However, I want to point out a few things that you have to look at. So first of all, we want to use a forward modeling run. So we have to set the operation mode to 0, which means forward modeling. Then we can define here in the second parameter called physics the problem that we want to solve. So in this case, we want to solve the 2D PSV problem. Yeah, and the other parameters you can more or less ignore at that point. So these are the modeling parameters that you have to define. And then you also, of course, have to define the acquisition geometry for which you want to compute synthetic data. So the next step is to define the acquisition geometry. And this is done in these two folders. So the receiver folder and the source folder. So if you go into the receiver folder and open this file receiver obc.dat, you can see that this is simply an ASCII file with two columns. Column 1 is simply the x coordinate of the different receiver positions, and column 2 are the depth coordinates or the y coordinates of the receiver position. So you can see the receivers are located every 20 meters. So here's the first receiver at x equals 800 meters, then 820, 840, up to, I think, 8,780 meters. And they are all located at the same depth, 460 meters. That is actually the sea floor. Yeah, as I mentioned before, we want to model a OBC cable. Okay, so these are the receiver positions, so they can be defined very easily. Now we need the source positions, so we go one directory up into the source folder, open the source OBC VSP .dat. VSP is actually not true, it's only a OBC geometry. And the source files are similar to the receiver files. The only difference is that in the first line you define the number of sources that you want to use. Then you have multiple columns. First column is the x-coordinate of the source, and the third column is the y or depth coordinate of the source. In this case we assume that we have airgun sources in 40 meters depth. And we have a shot point distance of 80 meters from 800 meters up to 8,720 meters, so 8.7 kilometers. The second column can be actually ignored because, this was actually used, this source file, also for a 3D version of the Denise code. And this would be actually the Z coordinate, which in this case, of course, is always 0 because we're using a 2D medium approximation. So there are no Z coordinates, but you still have to define these coordinates. Then there are additional columns, which I will discuss later on. The most important one that I want to mention here is the last column. This integer number here simply defines what kind of source are you using. Are you using an explosive source? Is it a directed source? So a directed source in X or Y direction. Yeah, so these are the fundamental source types that you can define, and as you can see in each line for each source you can define these characteristics individually. And this integer number 1 simply states that we want to use explosive sources for our seismic modeling. Okay, so we have now defined the source and receiver positions in these ASCII files. Now we need the model files itself, and we can simply copy them from the Denise benchmark folder. So we go into the start directory, and with CP we go 2 directories up, and you can see here now we have the Denise benchmark folder. So we will use Denise benchmark, then Mamusi2, start, and then we find here different models. Mamusi2 marine, Mamusi2 smooth 2, Mamusi2 start 1D, and Mamusi2 1D homogeneous. And we are now interested in this Mamusi2 marine, which is actually the true Mamusi model. The other models are actually initial models for the later waveform inversion that I will discuss in more detail later on. So we are only interested in the marine versions of the model, and we copy them into the start directory here. Okay, with ls we see now we have copied them successfully. So we have a model for the p-wave velocity, a model for the s-wave velocity, and a model for the density. Now we can check if these models are actually correct. Yeah, so if their sizes are, for example, correct. So this is always a good idea if the models are really consistent with the stuff that is defined in the parameter files. So what we will do next is we will check if the models are correct. So I go now here again on my desktop, NGP full waveform inversion, and into this directory, and I now try to store all the parameter files that we will use for this modeling run in order to reproduce them later on. So I'm creating here also a start directory where I will copy now simply the models from the NEC cluster. So we go onto the work directory again, then into Denise Black Edition, par and start, and here I copy simply these 3 models. Okay. Then we also have to store the receiver positions. Yeah, so I copy the receiver file from the receiver directory here, receiver OBC. Then I also store my source positions. Source OBC. Okay, and finally the parameter file that I use for the forward modeling. This is Denise Marmusi OBC. Okay, so with these files I can completely reconstruct the forward modeling part that we will do next. Yeah, so if I store these in this folder here, I can later on reconstruct it. And especially if I also store here my source code version that I used for this modeling run over here. So in this way we have now ensured that we can reproduce these results later on. So in 1 year, 5 years, 10 years, maybe also 50 years, I don't know. And yeah, before we start with the modeling, let's take a look at the models themselves, the Marmusi 2 model. And to do this, I have some visualization tools created. So if we look here into the Denise Black Edition par folder again, you see here a subfolder called Visu for visualization. And there is a Jupyter notebook called plot model underline PSV. And I simply copied it over here. And now let's start this Jupyter notebook. So I simply go to the Anaconda prompt again. As I mentioned before in the introduction of this course, we have to install Anaconda. And if it's installed correctly, you should be able to access here the Anaconda prompt directly when searching command. You cannot use here these traditional command window because all the Python packages that are coming with the Anaconda distribution are all only available here in this Anaconda prompt. So if this doesn't actually pop up, you have to go into your start menu, then into Anaconda, and then you can go here to Anaconda prompt. But actually it should pop up if you're using this Anaconda distribution. Okay, so then you are here in the command window and can go into the folder where you have stored all your stuff here. In this case I'm on my desktop. Okay, and then I go to the folder, how is it called? NGP for waveform inversion. And then into the folder 001 Denise Marmusi 2 run. Okay, then I start a Jupyter notebook. And as you can see, we can now start here this Jupyter notebook plot model PSV in order to check if the model parameters are all correct. And as I mentioned, it is really a good idea to use the Anaconda distribution for Python because it contains a lot of libraries. So what we need in this case are some graphical library, matplotlib, then NumPy for some numerical operations. Yeah, so that's basically it, what we need. So we can now use this Jupyter Notebook and execute here the cell using Shift and Enter, which now simply imports the different libraries. Then we have to define the FD grid dimensions. As I said before, we are solving the elastic equations of motions using finite difference approach on a Cartesian mesh. And so we need these modeling parameters, and of course they are defined in the parameter file. So if we open the parameter input file for Denise, you see the spatial discretization is actually defined here. So nx and ny are the number of grid points in x and y direction of the Cartesian grid, and dh is the spatial discretization of the grid, so the spatial grid point distance of two adjacent spatial grid points. So we only have to input these parameters now into our Jupyter Notebook. And of course I have already included the correct parameters here. So dh is 20 meters, nx is 500 grid points, and ny is 147 grid points. Then I also used a vp-min, which is I think only for visualization purposes. Okay, then we can define the fonts. So this is only an aesthetic problem, so to get nice looking pictures. And then we simply import a VP, VS and density model. So we first have to define a base name. So in this case we are located here in this directory. So here's our Jupyter Notebook, and the true Mamouzi models are here in the start directory. So the base name would be now start. And then we can define the different model files. So for VP, VS and density. In this example here I'm already using the full waveform inversion results. But because we have not run a full waveform inversion yet, we want to import the true model. So we have to use the true names, and so these are Mamouzi 2 Marine. Simply rename that and simply copy the name. And then define this as a string. So basically it's base name plus an additional string. Oops. Something like that. Point VP. So this is the name of the p-wave velocity model. Then we can do the same for the s-wave velocity model. So I simply copied that with Control C. With Control V, I place it here and rename it to VS, VS, and the same for the density model. Yeah. This is now name rho and the density model. Okay, so let's try this. So base name is start, and then we import the VP model, the VS model, and the density model. So no error messages occurred. And by the way, these models are defined as IEEE binaries. To be more precise, little endian binaries. And with these Python functions over here, you can import these binary files actually. Yeah, so first you open here the file, and then you define the data type. So this is IEEE floating point little endian. And then you simply read all the binaries from the file. This commando here, numpy.fromFile, and then here the file that you want to open. And this results actually in a vector. Yeah, but for display purposes it's better to really use a matrix. So what you can do, you can reshape the vector into a matrix and then display the matrix or the model itself in 2D later on. Yeah, so you have to do these operations. So first reshape, then transpose it, and then also flip up down the matrix in order to visualize it later on correctly. Then you define here the special axis, which is actually not 100% true. So the model starts not at 0 but at grid point DH. And yeah, so that should be sufficient. Okay. And here I created a short Python functions to simply plot the resulting model. So actually I plot all three models at the same time. So the VP, VS density model with this subplot function, using here imshow, yeah, to simply display it as an image. And here are some annotation stuff, which I will not explain in more detail. You can look for yourself what's going on there. Okay, now let's plot all these stuff. Yeah, here I'm plotting now the true model for VP, VS and density, and export the model also as a PDF file. Okay, so these are now the models. Okay, the true model is a little bit clipped, so let's... Okay, I think the dimensions are also not really that correct, so let's put it at 500 meters or something like that. 500, 500. Let's try this. Okay. Yeah, you can optimize it. So now you see we have a nice image of the true Mamouzi model for the p-wave velocity, the s-wave velocity and the density. So we have now checked if the dimensions of the model are really correct. So if we really have 500 grid points in x direction and 174 grid points in y direction. Of course, you now also have to check if the extension of the model is correct. So if the if the DH is actually correct, so the special grid point distance between the different models. Okay, there seems to be something inconsistent here with the y-axis, but you can take a closer look what the issue here is. Yeah, it's just a simple check, so you can try to fix this later on. Okay, so now we know the model is correct. We have not checked if the acquisition geometry is actually correct. I will show how to do this in the next tutorial. So I have written a nice Jupyter notebook to really produce all the necessary input files so that you can first check if all the parameters in acquisition geometry is correct and then create the models and the necessary input files based on that. Yeah. But of course I know everything is correct because I have used this model 100 million times before, so this should not be an issue. Okay, so now we come to the final part. We finally want to do some seismic modeling. So we have our models, we have our input files, and we can now start the modeling. How do we do this? We go simply into the par directory again of the Denise Black Edition code, yeah, where the Denise parameter file is located. And then we type in mpi run np, which is simply the number of MPI processes or the number of cores of our supercomputer that we want to use. And in this case we want to use 15. So what's happening actually is, when we go back into the model, so what's happening, the Denise code will actually decompose the model into different parts and then assign each part to a separate computing core of the supercomputer. Yeah, so each core then will, for its part that was been assigned, solve the equations of motions using the finite difference methods. And so this domain decomposition is defined by these two parameters here, nproc x and nproc y. So in this case it simply says take the MaMusi2 model and decompose it into 5 parts in x direction and 3 parts in the y direction. Yeah, and that means that we have in total 5 times 3, which means 15 parts of the MaMusi2 model. Yeah, so in x direction we then have decomposed the model into 5 parts and then 3 parts in y direction, which makes a total of 15 individual domains. And as I mentioned before, each domain will be assigned to a different core. So in total then we have 15 domains, which means we have to assign 15 cores in order to solve the problem. So that's the reason why we're using now here MPI run NP15. Of course, we could now change also this decomposition. However, you have to fulfill some conditions in order to do this, and I will discuss these conditions in more detail in the next tutorial. So for now we will simply use 15 cores of our 15,000 core supercomputer. Okay, and next we have to find the binary, which is of course in the binary directory. So we go one directory up with these /bin and then the binary Denise, and then we have to define the parameter file, which does not only include the modeling parameters but also links here the receiver and source position files and all the output that we want to create. And yeah, as I mentioned before, I will discuss all the parameters in much more detail in a later tutorial. For now we simply want to run this forward modeling problem, and that's it. So now we can hit enter and the Denise code will start the forward modeling run. So actually it will take each shot from the source file and then compute the forward seismograms for that. You can see it here. We have shot 18 of 100, and then it outputs the shot gathers for each shot. So we have here the shot gathers in the x component and the shot gathers for the y component. So the horizontal component and the vertical component shot gathers are exported to individual seismic Unix files, which we can then later on import into Python, for example. Yeah? So this will take some time, but we are already using now 15 cores, so it is much faster than using a single core, for example, on your desktop computer. Yeah, while this is running, let's take a look at the seismograms. And the seismograms are actually stored in the SU folder. So if we're going here back to the par directory, you see we have here a folder called SU, which stands for Seismic Unix, because the data is exported in the Seismic Unix format. And you now see here the different shot gather files. And let's take a vertical component, for example, for the first shot. And yeah, it's also a good idea to save it in a similar directory. So I copy it again here onto my desktop computer, to my 001 Denise Mamouzi 2 mod folder. And perhaps I should create also a Seismic Unix folder and then move this into the Seismic Unix folder so that everything is actually consistent. Yeah. Then let's take a central shot, for example shot 50. Copy that also into the Seismic Unix folder. And finally shot 100, which is, you see it, okay, also into the Seismic Unix folder. Very good. So now we have all these shot gathers. Let's try to visualize them. And to visualize them, we have to go again into the visualization folder of the Denise par directory and copy this Jupyter notebook called plot size, so seismogram plotting. And if we go here back into our Jupyter notebook, we see now we have here the folder SU, and we also have now here this notebook plot size. Perhaps I close this notebook here first, and then I open plot size. Now plot size also uses here NumPy, but it's also using an additional library that is not actually a part of the Anaconda package, and that's called ZecY.io. So if you search for ZecY.io, you should find the GitHub page. Yeah, it's here. So this is a fast Python library to import and export actually ZecY and SU files. So it's really handy actually. And it's also quite easy to install. So if you're using Anaconda, you can simply install this using pip. So what you have to do is you have to open the command window, Anaconda prompt, and then you simply type in pip install ZecY.io. And then hit enter, and then it will install this ZecY.io library, which you then can import into your Jupyter notebooks, and then import Seismic Unix files, ZecY files. That's really, really nice library for Python. So let's import this Python library. And here I've now added a short code cell in order to import our Seismic Unix files and then visualize them later on here. Yeah, so first we have to define again the path. So the plot size in my case is located here, and the seismograms are in the SU folder. So this is simply SU. And then we have to define here the base name of our Seismic Unix files again. So this is Denise Mamouzi, everything in capital letters, and of course I already prepared that. And as a nice touch, I also added the option to simply define here the shot numbers, and then the shot numbers are added here as a string, so that you only have to change the shot numbers in order to import different shot gathers. Yeah, and this is how you import actually the Seismic Unix files with ZecY.io. Okay, so then you can here get the basic attributes, get the numbers of traces and number of time samples. From the number of time samples and the sample interval, which you can get from the header files of the Seismic Unix file, you can calculate here the temporal sampling, so the DT, and from the temporal sampling and the number of samples you can calculate the time array. Then you can also get the offset of each trace and the source position of each trace. I think in this case I only used the offsets, but okay. So this is how you import these information. Offsets then would be in meters, I think. Yeah, would be in meter. And yeah, so this is the most important parameters to plot this. So you need the offsets and the time to correctly plot the shot gathers. You have a short function to plot the shot gathers. You define a clipping value, which is simply a fraction of the maximum amplitude, of the maximum absolute amplitude of the shot gather. And Vmax is the positive value and Vmin is the negative value. So that it is centered around 0 correctly. And with plot imshow you simply plot the seismograms. Annotate all the stuff, okay. Have I already imported it? No. So let's first import the first shot and then we can simply plot it. Okay, the clipping is not optimum, so we can reduce the clipping value here. So that's much better. Perhaps even a little bit more. That was too much. Let's try 5 times 10 to the power of minus 2. So this seemed to be a good compromise. So this is a shot gather for the first shot of the ocean bottom cable. So we have a maximum recording time of 6 seconds. And maximum offset is something like 8 kilometers. That seemed to make sense. Yeah, if you remember, the source and receiver positions were approximately in this range. Yeah, and what you can see is a very complex wave field, not really surprising because the underlying model was also quite complex. And yeah, what you see is actually here a refracted, a direct wave, and then also some refracted waves. Yes, we see the slope of the first arrival is changing to some degree. And then you can see multiple reflections. Actually, there are also a lot of internal reflections in the water column. But then also very complex wave fields. So you see here also a lot of diffractions, for example. And yeah, so really, really complex wave field. So let's take a look at another shot. For example, shot number 50. So this is a more central shot, which still looks complicated. And shot number 100 should be the shot from the left. And as you can see, this is actually a shot position here at 8,000 something meters. The offsets seem to be not correct actually. I think this is not working because I simply defined the extent from min to max. This is actually not working. So the offset axis is actually wrong. So you should try to fix this actually, because this simply plots here an extent of the image. So this, instead of the offset, it might be better to actually use the receiver position or something like that. So you can try to get the receiver position from your Seismic Unix file header and then plot the seismogram or the time over the receiver position. Then it would be correct, but the offsets here in this case are not correct. They are correctly imported, but I did not plot them correctly here. Yeah, so that's really important to keep in mind. Okay, so this seem to have worked quite nicely. So we have now synthetic seismograms for our Mamusi 2 model. So finally, I want to mention another thing. I simply used this MPI run on the login node of the NEC cluster. So this has two major disadvantages. So first of all, this login node only has 32 cores. So the maximum parallelization that you can use by the domain decomposition is using 32 cores, which is not really much actually. So you should use this approach only to test your code, but not actually run the code for 7 days or something like that. Yeah. So in order to use the cluster correctly, you have to submit a so-called batch job. And I want to shortly explain how to do that. So we are now in the par directory of Denise Black Edition. We go one directory up, and you can see here this folder jobs. And this is exactly what it sounds like. So this is batch. This contains a batch job script. So if we edit that, you can see this is a so it's called batch job script. So it's actually only a shell script. And it defines different parameters for the modeling or inversion run that you want to run on the supercomputer. So first it defines a job name. In this case we call it simply Mamusi. Then it defines the different computational resources that you want to use. So first of all, you only want to use one node. So the cluster is decomposed into different nodes, and each node contains 32 cores. And so tasks per node can be, for example, 30 or 32. 32 in this case doesn't actually work. I will explain why in the next tutorial. Then CPUs per task is 1. Which simply means that we are using one core for each task. So this would be important if we would also use multi-threading or something like that. But we will not use it here because Denise doesn't really support it at this point. So we're using one node and 30 cores per node. So that would be 30 domains for our Mamusi 2 model. So we can decompose the Mamusi 2 model into 30 parts. What I have run previously were 15 cores, so or something like that. But to save more computation time, you can also use 30. Then you define the maximum memory, so the random access memory that you want to use. You can use 100 gigabytes. It's actually far too much for this problem, but it doesn't actually matter. Then you can restrict the computation time. This is restricted here to 24 hours. And then you can output different text files. So for example, you can pipe the output into test point out, and if an error occurs, you can output this into the test point error file. And finally, you have to define where do you want to run the code. So cluster means that we're using the parallel NEC cluster using MPI. There's also an option to use another part of the cluster, which is a scalar cluster. So you can use their OpenMP, for example, so if you want to vectorize your code. And the third option is to use a GPU subcluster. Yeah, so we have a few graphics cards also in there where you can run your code. But in this case, we want to use MPI on this simple Linux cluster. Yeah, number of threads is if you want to use also OpenMP, but we don't want to use it here, so we set this to 1. Then we have to load the Intel compiler and the Intel MPI library. And finally, we have to start the Denise Black Edition code. So we first have to go into the par directory of this Denise Black edition code. So this should depend on your, no, it should not depend on your user, it should depend where you located all this stuff. But you can use this work link and then use this Denise Black edition /par. And in this case, this should be correct, but you have to check it for your case. So you don't have to use actually the whole description of the path, but you can replace this part here simply by the work subscript here. Okay, and then you have to use exactly the command that I used before when I was running the code on the login node of the NEC cluster. So mpi run mp15 in this case, and then the location of the binary file and the name of the input file. So this is actually what I've done here. This file is actually not necessary for the forward problem. Yeah, and then you can pipe the output also into this Denise.out file. Okay, now we are using 30 MPI processes instead of 15 as in this example. So before starting this job file, which we should also save, yeah, so file save or Control S. Before we can submit this job file, we have to define the new domain decomposition. So we go here into the Denise Mamusi OBC input file, and instead of 5 times 3 equals 15 CPUs, we now want to use 10 times 3, which means we're using 30 CPUs. So this is really important. If you don't, if these parameters here are not consistent with the parameters in the batch file, you will get an error message and the batch job will be cancelled. Okay, so this seemed to be all correct. So let's submit this job. So we go back into the jobs directory, and with sbatch we can now submit the job script to be more precisely, and with sq we can see the status of our job. Unfortunately, not only the status of our job, but the status of a lot of jobs. And you see there are already a lot of jobs on the NEC cluster. Some are waiting and some are running. And you see most of the users are only using one node, and I assume only one core, because they are running here thousands of jobs in parallel. Yeah, so that's quite interesting, but actually we are also interested in the state of our own job. So what we can do is we can use sq again, but then use the grep command to grab only the output that contains sungw, which are only the jobs related to the geoscience department. And yeah, so these are all the jobs that are currently running from the, basically most of these are geophysicists, so they are running here some waveform inversion jobs. And unfortunately I don't see our job, which means there was some error in the job description. Okay, let's try to find the error. So let's take a look at test point error. There's no output. Test point out. Also no output. Then we go back into the par directory, and there's a Denise.out, which shows to what extent the code was actually running. You see here it writes a lot of parameters, and then we go here to the Oh, so the reason why there was no drop is because it was already finished. Okay, so this was actually a quite bad example. So the drop was so fast that we didn't realize that it finished correctly. So we have now our Seismic Unix files here. If we look at this timestamp, yeah, that was quite recently. So, as you can see, on 30 cores, it's running much faster than on 15 cores. The reason is also because you do not interfere with all the work that the other users are currently doing on the login node. Okay, but that was a little bit too fast, so let's try it again. So sbatch Denise Marmouzi NAC. Then SQ again. Where's SQ? Here. And now we see our job is running. Here Sun GW331. This is my username. And it is running currently on one node and 30 cores. You don't see the cores here. This only tells you how many nodes you are using and the elapsed time. And you also have here a job ID number. And for example, if you want to cancel your job now, because you found an error in your model or something like that, you can do this with scancel and then define the job number. Yeah. So this would cancel now our job that we are currently running. Look at it again. Yeah, so it's cancelled, or what's more likely that it was already finished. So we go back into the par directory to Denise point out, and then we see if it was finished or if we really cancelled the job. Okay, so we go down here and you see it finished after 42 seconds, or 44 seconds more precisely. Yeah, so but this is the basic approach that you would use to really run the computationally intensive stuff. So you would not run it on the login node, but you would submit a batch job for that. So finally, we have reached the end of this quite long tutorial. So let me shortly summarize what we have learned in this tutorial. So first of all, we have learned how to model seismic wave propagation for the quite complex Marmouzi 2 model using the Denise 2D PSV module. And after getting some modeling result, we also learned how to visualize, first of all, the model and the synthetic seismograms using some very nice Python functions. And finally, we also learned how to run the Denise Black edition on the NEC cluster using the batch processing system Slurm. Okay, so these are the most important aspects that we learned in this tutorial. And as I mentioned before, it is quite essential that you can accurately solve the seismic forward problem in order to apply later on the full waveform inversion. So this is really the essential core of the waveform inversion. If you cannot predict the seismic waveforms correctly with your synthetic data, the waveform inversion will actually fail. Yeah, so this is really important to understand, how to really do accurate seismic modeling. So this was just a short overview on how to run the Denise code. In the next tutorial, I will describe in much more detail all the individual modeling parameters and their impact on the modeling result. So finally, I want to thank you for your attention. I'll see you in the next tutorial, and bye for now.